So hello everyone. Want to get started exactly on time. Thank you all for coming. So it's a good crowd here. I wasn't expecting, or wasn't sure how many people to expect really. So it's a little bit of a different type of talk. So I hope I haven't missold it too much. I should also say I've done this talk a couple of times before as well, and they were both 2-hour long talks, so I've had to abridge it a little bit. I'm going to have to rush a bit, which means cutting some bits short, including my introduction, so I'm going to get straight into it, because I don't want to rush too much either. So I'm Phil Nash. I've done lots of talks over the years, so this one is a little bit different. And I wanted to start by, very briefly at least, addressing my title slide. You might be wondering, why is there a car up there? Well, this is the Oldsmobile Cutlass Supreme. Came out in 1989. I'm sure everybody remembers it well. Oldsmobile, originally Olds, had been around for about 100 years at that point, and they were starting to lose market share to other newer, trendier brands. And so they came out with this genius marketing campaign. This is not your father's Oldsmobile. Maybe some of you remember that. It's sort of survived as a bit of a meme these days, to where my title comes from. But the idea was, this is something new, fresh. It's going to appeal to the next generation. And unfortunately, it backfired a bit. It turns out it wasn't actually that new. It was very similar, just sort of a bit warmed over. And it failed in the market. And Oldsmobile were pretty much gone within a decade of that. What's that going to do with C++? Well, there's at least one, possibly two points in C++'s history where it's had a bit of an Oldsmobile moment, where it's been around for a long time, it's got to appeal to a new generation. Is it going to survive? And we're going to address at least one of those, possibly the second one if we get time at the end, to see whether that's actually happened or not. I should also say, this was a product of the 80s, unnecessarily sexist and ageist. 2 for 1. I managed to get rid of the sexism part, but I added an extra generation into mine. Not out of any sort of judgment, but just to say, well, C++ has been around long enough that if you were there at the start, you are old enough to be a grandparent these days. Has anybody been using C++ since before 1992, out of interest? Just one person. Thank you. That's when I started using it. So one of the oldest people to use C++ in the room, or using it for the longest time. Okay, so let's get straight into this. And I want to go right back to the dinosaurs. Well, figuratively speaking anyway. I want to do a little bit of a prehistory of C++, the historical context that C++ was born into, just to give us a bit of a feel for what this language is actually all about. I'm going to do that by means of a bit of a family tree and timeline. So it's really rooted in the Algol family of languages. There were sort of 3 languages that came out in the late 50s, all around the same time, Lisp and Fortran with the other ones. And Algol sort of survived through CPL, BCPL, B, and then C, 1972, on this left-hand side. And we may have heard of some of the other languages in between, but probably don't know a lot about them. I don't know if anybody here has actually used any of those other languages, but we all know C. C survives to today, well represented even at this conference. So that's the history of that line. And on the other branch, we've got Simula there. I'm sure we recognize the name Simula. Isn't that where we get all the OO ideas from C++ into C++ from? Which is sort of true, but not Simula 1. Simula 1 was just about simulations built on top of Algol. Simula 67 was quite a stark reimagining of the language, and that's where all the OO features, classes and inheritance and that sort of thing all came in. 1967, same time as BCPL. Interesting timing, because late 70s, those 2 languages were being actively used by a certain Bjarne Stroustrup, might recognize the name, in his PhD thesis. And he was using both languages side by side. And his observation was Simula 67 had all of these really nice high-level abstractions that he really liked and he felt would be great for building large-scale applications. BCPL, though, was much lower level and much faster, had the performance that he really wanted. Simula didn't. but it was so low level it's just a bit too tedious to write, and he couldn't really see it scaling. He really wanted the best of both worlds. So after he finished his PhD, he went to work at Bell Labs. He started on something called C with classes. I'm sure you've heard of this. The original version really of C++ really just rolled those OO features from Simula on top of C, literally just a preprocessor really. And that was just an internal project at Bell Labs, iterated for a few years. Mid-80s, new version came out with a whole load of new features as well, and a new name, C++. And now this was open to the public as well. So this was really the birth of C++, 1985, but 1979 is when it all started. And the historical context is there because I think it's really important to get a feel for what actually led to the creation of this language. It was a desire to get what we now call zero-cost abstractions. We want those high-level abstractions, but we don't want to pay for them. And that actually leads to the second part as well. If there is a cost, we shouldn't have to pay for it. We should be able to opt into it. We know both these terms, I'm sure. They're still a thriving part of C++ today, but they've been there right from the start. This is really what has shaped the language. Zero-cost abstractions, and don't pay for what you don't use. So I'm going to talk a little bit more now about some of the features of the earliest versions of C++ and get a feel for what that language is like, maybe compared to what we have today. So let's go into the next era now. But we're going to look at pre-standard C++, starting with C with classes. As I say, just got those OO elements from Simula. And actually even the polymorphism, it was very basic to begin with, much later, more towards the mid-80s C++ era. We got virtual functions. They actually came quite late. And then C++, 1985, added actually quite a few extra features on top of that. References came in then, inline functions. Templates, exceptions, namespaces, they're all early 90s, or maybe like turn of the 90s, so quite late really. That was all pre-standard C++, right up until towards the end of the 90s. But around the turn of the 90s, Bjarne felt that this really needed to be standardized, and a committee was formed. So spent most of that decade standardizing C++. So we got C++ 98. The big new feature of C++ 98, of course, was the STL, the standard template library, which is very familiar to us now, but back in 1998, even though it had actually been around for a while as third-party libraries, for many of us, 98 was the first time we really got a taste of the STL. It really was revolutionary, a very different way of working. It really changed the way we use C++. And we'll look a little bit about why in a moment. All of the other things were touched as well to some degree or another. It really did feel like a new language. Alexandrescu's book, Modern C++ Design, was actually based on C++ 98, and even like early 2000s, he was saying, actually no compilers can support this yet. It took a while to catch up. It was a big release, a very first release. But I actually want to focus on something that came in much earlier. Back in 1985, the first version of C++ introduced references into the language. Why do I want to focus on this? So I think this really sort of sets the tone of where both some of the power but also complexity of the language comes in. I'm going to skip through these slides a little bit because I'm sure you know how references work and how they compare to pointers. Maybe to stop on this bit, comparing pointers and references side by side, because they do share some common traits. They're initializable and assignable, but that's it. All the other capabilities are unique to pointers. They seem to be the more capable concept, the more powerful concept. But actually the power of references comes from what they don't do. That gives it simplicity and guarantees. In many ways, references are the superior choice, unless you need one of those other things, which hopefully is fairly rarely. Nullability we can now get with stood optional. We don't have to resort to pointers for that now. Different syntax just gets in the way. So we would prefer references, but Again, a common theme of C++. We're getting a new feature, replaces something old, but we still have the old thing as well. Now we've got both. Part of the complexity of the language. Talking of which, introduce const in, multiply that with pointers, you get all these different ways of doing things. This is only one level of indirection. I'm not even going to talk about pointers to pointers, or the fact that you can put the const either side. That's another talk. Compare that to references, you can see it's a lot simpler, much easier to reason about. Well, whether you use pointers or references, they are just ways of adding a level of indirection over values. So we have value types, and of course the value could be const, as can the pointer, which is also a value. But at the center of this is the value. C++ is inherently, by default, a value-based language. Maybe we don't think of it that way, but actually a lot of language features are really just in service of giving us value semantics. Value semantics were really an inherent part of early C++ and to this day. Gave us things like RAII. Sure you know, RAII stands for resource acquisition, is initialization, a very powerful concept that is almost unique to C++, at least amongst modern mainstream languages. Some other languages sort of approximate part of it, but it's only really C++ that gives us a whole range of value semantics around that. We usually focus on what you can do in destructors. It's one of the more unique things. That determinism of the destructors. We put one of these things in different scopes. We know exactly where that destructor is going to fire. We can take advantage of that. It's really powerful. We miss it when we go to other languages. So we can be very specific about what's going to be printed out here, for example. Again, I'm not going to dwell on that too long, but definitely a very powerful part of C++. But it's not just the destructors. Value semantics includes these custom constructors, copy constructors. We've also got move constructors now, we'll come on to that. Assignment operators. They're all part of what the power that C++ gives us over how we use the language. Fairly unique to C++ in that respect. So let's come back to C++ 98. We mentioned the STL, gave us vectors for the first time. We had other third-party libraries that may have approximated this, but vectors were still a big step forward, as were the other containers. Because now we can manage all of the memory using those RAI techniques. We've got generics with templates, so we don't have to have a different version for each type. It's all there packaged in a simple type that we can treat as a value. So it's a value type. Again, we take it for granted, but that's actually a really powerful feature. And it's still low level. We're not really paying much, if anything, for all of those conveniences. Great. Then we actually try to use it. So C++ 98, if we want to load up one of these vectors, all you can really do is push back. There were some third-party libraries that tried to make this simpler, but really you're doing a lot of pushing back. So it gets a little bit verbose if you do a lot of this. And you still sort of have to know about the memory management under the hood. There's going to be maybe a couple of allocations there. If that matters, well, we can reserve ahead of time. So, yeah, we're not paying for what we don't need, but it is quite low level. All right, but we've loaded up our vector events. One allocation, so far, so good. Let's introduce another vector. This time it's a vector of strings. Stood string, another value type managing its own memory. Great. Let's say we want to convert all of those integers into strings, put them in this second vector. Well, we know how big it is, we can use reserve. And then we're going to iterate over our original vector. We could have done it with C-style indexes, but the idiomatic way in C++ 98, of course, is to use iterators. It's the powerful abstraction in C++ 98, in the STL. Going to gloss over exactly how powerful it is. I'm sure you're familiar with them. But to use these iterators, you probably have to put them into variables. And in C++ 98, that means spelling them out longhand. It's a subtype of, or a type within the vector, and then because the constness is actually the thing you're referring to, you've got to put that in the type name as well, and it looks like this. If you've done old school C++, you're very familiar with this. These type names are so long that we usually put these loop variables outside of the loop because we couldn't fit them in. Can't even use loops properly. But it's idiomatic. Let's do the string conversion then. So we got string stream. That was also new in 98. Interestingly, we had stress stream before that. Anybody remember stress stream? So it's actually still in the standard. I think they're removing it in 26, finally. We finally got all the pieces necessary to replace that. But stress stream's good. We can dereference our iterator, put the int into the string stream, do .str to get it out. It works. It's not the most efficient way to do it. If you care about the performance here, you're probably going to write your own or use another facility. But as a go-to, it's actually pretty good. Not too bad. All right. And then let's iterate that loop. And with this time, we'll use an index just because we can and print things out. We're going to use std_cout from the IO streams library. So IO streams actually was one of the earliest libraries in C++. I think predates 1985's original C++, in fact. Quite an old library now, but still going strong. We'll come back to that one. Okay, we achieved it. Quite a bit of code, but a lot of conveniences as well. Just for fun, how would we do this in Python? This does the same thing in 3 lines, and it's quite expressive. We're not quite there yet, but we're doing okay. I'm sure it's faster. Let's have a look at classes. So again, I'm not going to spend too long on this. I'm sure you know how classes work. But this one has a string and a vector of strings in it. And we've got a constructor. And it's going to take a string and a vector of strings. And again, idiomatically, we do that by const reference, because that's going to be more efficient. But then we copy them into our members. Okay, that's fine. Been doing that for years. And now we've got some accessors, just some member functions that will return us some of those. Typical class. But because we've got that vector in the constructor, it means we're going to construct one of these classes, we're going to have to instantiate a vector outside, load it up using pushback or whatever, and then we can use that, pass it into our constructor where it's going to get copied. At least a string we can do in line. So that's fine. And this is the value type. By default, we have the value semantics in C++. And we can use the dot operator to get at our member functions. Fine, all very familiar, I'm sure, if it's a value. But we might want to create these on the heap. So we have the new operator, of course. Now we get a pointer, use a pointer. Have to use the arrow operator at different syntax. A bit ugly, but we can live with that. And now it's on the heap. We've got to remember to delete it as well. Notice I'm saying pre-std C++ down there. Even before C++ 98, there were third-party libraries for doing what we can now call smart pointers. Uses those RAII techniques to clean things up for us. But in C++ 98, we've got that in the standard. We've got auto pointer. Great. Now we can use the new keyword, but pass off that pointer to auto pointer, and it will manage that memory for us. And we still get the pointer semantics to get to the member function. Brilliant. Solves all of our memory management needs, doesn't it? Until we come to copy it. If you copy an auto pointer, what happens? Well, that will compile, and it's going to transfer ownership from the outgoing auto pointer to the new one. Well, sort of looks familiar if you squint, but remember this is a copy operation. It's a little bit surprising for a copy operation to mutate the thing you're copying from, but a very powerful technique nonetheless. A lot of promise here, but also very dangerous. In fact, so dangerous that if you try to put one of these into a std vector, well, first of all, you can't. If you could, it wouldn't work. You'd lose objects if they get moved around, and that's why we had to put specific code in there in the standard to say you cannot allow an auto pointer in a std vector. Think about that for a moment. We had to design the standard in such a way that you couldn't use one part of the standard with another part because it was too dangerous. lot of power, a lot of danger. We'll fix that, but that was C++ 98. Obviously, there's a lot more we could talk about. I've only got a few minutes. So 1998 came and went. We got the new standard. And then it was 5 years before we really saw anything else out of the committee. We got C++ 03, not really a new standard. You think of it more as a patch on C++ 98. In fact, you'll often hear people say C++ 98/03. Rolls off the tongue. As if it's like a single standard. Because 03 did actually fix a lot of niggly little things. It was really just a lot of fixes and refinements. For example, std vector. The memory in std vector was not guaranteed to be contiguous in C++ 98, which seems ridiculous. And all implementations made it contiguous. People relied on that, so 03 made that standard. And now we can rely on that. So we never really talk about C++ 98. We talk about C++ 03. Why would you use 98? Okay. At this point, Moore's law was still in full swing. Processors were getting much more powerful year over year, and no new standard was coming. There was a lot of talk, but C++ was pretty stagnant. So other languages like Java, C#, maybe even Python, were starting to take a lot of market share where C++ had previously been reigning. Because the performance differences didn't matter so much anymore, but the productivity, the high-level abstractions did. So this is where we approach our Oldsmobile moment. And in fact, the years went by. There's a lot of talk about it's all going to be worth it because we're going to get concepts, and concepts are going to completely change the way we write C++. And lots of other stuff, but still no standard. We were talking about C++ OX, because it's definitely going to come in that first decade. And we got towards the end of the decade, and we said, actually, it's hex. We've got another 6 years yet. And briefly, we talked about C++ 1x, let's be honest. But only briefly, because then suddenly C++ 11 was here. Finally. But is it too late? Is it going to be that Oldsmobile moment? A lot of promise behind C++ 11. It's going to completely transform the language, modernize it. It's going to be great. But it's been a long time, 13 years really, since the last release. Moore's law, though, had now dried up. Well, was really slowing down. Very small increments in processor power year on year. And actually, there was a big shift towards multi-core, so parallelism becoming more important. Fortunately, well, previous C++ didn't have a thread-aware memory model. C++ 11 it did. Low-level threading primitives, the promise of higher-level threading libraries, concurrency libraries coming in the future. Not there yet, but they're coming. So at least the shift back towards a focus on performance was actually C++'s opportunity. Here's the new standard. Is it going to be good enough and be up to the challenge? I would say it didn't happen overnight. It took maybe a few years, perhaps even into the C++ 14 timeframe. But at least from my memory, I started to see more and more new generations of people starting to take C++ seriously again. And certainly by the time C++ 17 came around, it was a transformed community. I think we avoided the Oldsmobile moment, partly out of luck, but we did it. We escaped. So, what was it in C++ 11 that made it so impressive? Let's have a look. So, we looked at this example earlier with the vector, loading it up, converting it to strings, all of that, very tedious, but low level. We pay for that in lines of code, really. Let's have a look at the first bit. First of all, loading up with all the pushbacks. Little thing, but C++ 11 gave us the initializer list. And not perfect, it's not free, small cost, maybe optimized out, in this case probably is, but so much nicer to use, especially for this sort of code. Nice little win, okay. What about those iterators though? We wrote lots of this sort of code, and we hated it. Well, we grew to love it, I suppose. Of course, C++ 11 gave us type inference. Useful for a lot more things than this, but the perfect application, because now we don't have to spell out those big long names anymore. And we never cared about that type anyway. Perfect. Great. And in fact, this is now so small, we can put that back in the loop. So that's nice. What about the string conversion? Even that got some attention. We've now got std2 string. Again, it's not necessarily the most performant, but it's at least as performant as the old string stream approach. So again, as a go-to, great. Quite often we want to do that sort of thing. Now it's a one-liner. Definitely getting there. And of course, you're all saying it, we have the range-based for loop. We don't even need to see those iterators anymore. We can just let the compiler do that for us. We don't have to dereference the iterator there. Much cleaner. Now, don't think he's here, but we do have Sean Parent on site this week. So I'd better mention that actually you shouldn't be writing raw for loops. We need algorithms. And of course, you've been able to do this since C++ 98. In fact, the only bit that really changed is the bit in the comment there. So we brought the iterators back and put a back inserter in there. But the bit that we actually call to make the transformation in this case, well, it could be a function pointer, but idiomatic C++ 98 had us writing what we call function objects. Just a structure, a class with a public call operator, and that's what's going to get called on each iteration of the loop. This is quite nice, actually, not least because now the compiler can see all of that code and inline it. And in many cases, we can actually get better performance than the equivalent in C as a result. Things like std sort in particular. But, it's quite a bit of boilerplate code. We did it, but could also be better. C++ 11, of course, we've got lambdas. And now we can do the same thing in line. And when I say the same thing, I mean that quite literally. This lambda is exactly equivalent to this struct. And sometimes we forget that. It's actually a useful way of thinking about them, particularly with regard to lifetimes. But really what you're defining there is a class with a call operator and potentially members. So if you have a closure, so something in the captures list, you can think of that as arguments to the constructor of the class that's being generated. So that's really nice. And we even get fine-grained control over that. So that was by value. We can capture it by reference. We can capture everything by value or reference. Quite a lot of control. But actually, most of that complexity is coming from the fact that we have references in the language at all. So a bit more verbose than other languages, but still a lot better than where we were. So lambdas were a really big win for C++ 11. Really helped to modernize the image of the language and its use. So great, really nice. What about this big problem? Auto pointers. Deprecated in C++ 11. Great. Removed in C++ 17. I don't know if any compilers have actually removed them yet, but they've been removed for a while. That's how dangerous they were. And of course we have direct replacement, drop-in replacement really, std unique pointer. I'm sure you're familiar, but works exactly the same way, except for that copy. We tried to make a copy. It's deleted. Deleted constructors, also new to C++ 11. You can't actually copy an auto pointer. Doesn't make sense. It's a move-only type. But you can move one. Also new to C++ 11. Move semantics, and in particular, R-value references, which you can get from a temporary, something that's about to go out of scope, or explicitly using std move. Now we invoke the move constructor of std unique pointer, which will take ownership in a much more controlled and expressive way, which means std vector can hold them, which is great. Obviously still some dangers, but nothing we can't manage. So that's good. If we look at that class again, we could add our own move constructor. Something like this. More importantly, instead of taking things by const reference, if we're going to store them anyway, we should probably take them by value most of the time and then move them in, which will often be more performant. So we're getting higher level abstractions and more performance at the same time, which is great. Moving in the right direction. So that's C++11. A lot went into this release. Big release. Even here, there's a couple of things I hadn't talked about yet. Variadic templates were quite a big deal. Perfect forwarding. Const expra. We've got the first version of const expra. Very limited in 11. Just one line, single return, no conditionals, variables. But it's a great start, still really useful. We're going to see more about const expra. Shared pointer, unique pointer up there in green, because they're actually the only library types on this slide. Loads of other language features. I'm not even sure if that's all of them, but quite a few. And then loads of library features as well. It's a massive release. So yeah, we waited 13 years, but we got what we paid for. But we also realized we didn't want to make that mistake again. We're not going to wait another 13 years. So we changed the model for standardization. Instead of waiting for things to be ready for a new standard, then we set a time limit. So every X years, which turn out to be free, we're going to have a new standard. And whatever's ready goes in. If it's not ready, it gets pushed back. The so-called train model. Get on the train or you miss it. So we knew, even back in the C++11 time frame, there's going to be a C++14. There's even going to be a C++17. And we can even start thinking about what's going to be in them. And that sort of takes the pressure off a bit. So when it comes time for C++14, it's a much smaller release. And that's okay, because we've got C++17 coming, that's going to be the big one. But C++14, certainly bigger than 03, but still more about refinements, fixes, and a few nice features. Auto lambdas is actually quite a big deal. Basically lambda templates. Some fixes, make unique, should really have been in 11, but we got it eventually. Const expra actually expanded quite a lot. You can now do variables, loops, conditionals. It almost looks like normal code. Still some limits, but a lot more capable. All came in 14. Plenty more as well. Shout out to Stud Exchange. I don't know if you can see that down there in the corner. Often overlooked, but actually very simple but quite powerful feature of the standard library. We should probably use more of it. Plenty more. Not a bad release, but a small one, and that's okay. Because 17 is going to be the big one. You know, we're going to get concepts, coroutines, ranges. They're all going to be in 17. Of course, you all know we didn't get any of those things. We found that out quite late, and there was a lot of disappointment. Is 17 just going to be another little small release like 14? That's a bit of a letdown. Turns out we got quite a lot, and it took us a little while for that to sink in, I think. Let's have a look at some of them. So our example of the stud vector from earlier. Well, we've got all our ints there in the initializer list. We've got type inference in C++11, but we still have to spell out the int here until we get ctad. Class template argument deduction. If we can deduce the type from the constructor of a template, then we don't have to spell out the template type. Sometimes you get that for free. More often, you're going to have to write some explicit code to handle this. So it hasn't quite taken off as much as we would have liked. A little bit more fiddly to use, but still, it's a nice feature. It makes things a bit nicer again. You have to write less explicit code that you don't care about. I'll get a thumbs up. Let's have a look at this example. So rather than converting integers to strings, we're going to do it the other way around now. Parse a string into an integer. We're going to use a string stream again. Again, not necessarily the best way, but it's there in the language, in the library, so we'll go with that. But we're taking a stud string. Again, we're going to do it by const reference because we're not storing it anywhere. So if we take it by value, we're going to pay the cost of an extra copy. We might still pay the cost of an extra copy if we pass in, say, a string literal. A character literal. But C++17 gives a stud string view. And now if you give it a stud string, a character literal, maybe one of your own string types, or third party, or something else, all it's going to take is the pointer and length, and it will just work with no overhead compared to, in fact, maybe even less overhead compared to the const ref, depending on how it optimizes. Big win, or it can even work with substrings, of course. So that's nice. But if you've got a function like this, you're probably going to want some error handling because you're not always going to pass strings that have ints in them. So that's a little bit of a problem here. We probably don't want to do exceptions. That's probably not the best approach for a function like this. But the return channel is already taken up by the integer. So we'll often resort to tricks like this. Return a Boolean to indicate the error and take the actual result by reference. It works. We've been doing it for a long time. At least that's better in 17 because we can use no discard. So we have to look at the return type, at least consider the error handling. But of course there's a better way in C++ 17 because we get stood optional. A type that represents a value or the absence of a value sort of mixes that Boolean in. And now if we don't have a value we get a null opt. And in usage, looks like pointers. We can test it in an if statement, dereference like a pointer to get the value out, or it's an error. If you actually want to know what the error is though, well, it doesn't give you that. So if you want to use these for error handling, it's still a little bit missing. So you might use stood variant, which you also got in C++ 17. I wouldn't recommend this actually. Stood variant is actually very, very useful. Represents one of a range of types. You could use it for error handling like this. This part's not too bad, but if you come to actually use it, there's a few ways you can use stood variant. They're all a little bit like this, quite verbose. This one I'm using stood holds alternative and then stood get. I've actually had to put the result on its own line as a separate statement because then I've got to do holds alternative here. It's quite verbose. Well, we did get the init statement in C++ 17, so we can at least move that first statement into the if. Now the variable is scoped to the if statement. But still, it's a bit too verbose. Variant's not a good solution. We'll look at a better solution later. Just setting that one up. Lots more we got in 17 that we don't have time to look at, including structured bindings. Quite a big feature. Came in quite late. We won't talk about that now. Fold expressions to make variadic templates easier. Even more const expra. I think we got const expra lambdas in 17. And if const expra. Actually making a compile time branch just with normal looking code within a function. So much template metaprogramming is no longer necessary with if const expra. It's a really big win. All that came in 17. And there's plenty more, it's just the highlights. So not a bad release after all, but we didn't get those big features that we've been waiting for. So that brings us to C++ 20. Now at this point, those of you that are working every day with C++, maybe you've just moved on to C++ 20, or maybe you haven't moved on to it yet. This is still taking a little while to reach the mainstream, and I think we're just crossing a threshold now, maybe. It's a big release again. In some ways, maybe even bigger than C++ 11, certainly in size of the features. I can understand that some people are taking a little while to adopt it. So let's have a look at what actually made it in. Now, this is the slide as I had it when I first gave this talk, when C++ 20 was not quite done, but all of these things have been voted in. You can see the odd one out. So contracts was on here. It had been voted into the standard at the point that I gave this talk, and then shortly after was taken out again. We didn't get contracts. So like concepts in C++ 11, didn't make it in. Contracts didn't make it into 20. But we got everything else. And that was actually really big. Lots of big features. Coroutines, concepts, not quite the C++ OX concepts, but still really powerful and really worthwhile. Ranges, a big evolution on iterators. Modules, that's going to solve everything. I promise. Spaceship operator, one of the few features to go into the standard that actually reduces the amount of wording in the standard overall. And even more const expra. Actually, I don't even remember which bits went in. I think it was memory allocations and try catch, maybe. We can actually finally get things like strings in vectors in const expra. Lots more, of course, but these were good highlights. Certainly the big things. I want to do a couple of little code examples to try to give you a flavor. So here's a function, a template that tries to print a container. The implementation, it's not perfect. It's got some downsides, but don't worry too much about that. It's more that signature I want to look at. You can take any container because it's a template. And so, sure enough, if we pass it a vector of ints, like the one we had earlier, it's going to print them out quite nicely. Great. But it's a template. It can take anything. And even something that's not a container, like an integer. And of course, we're going to get a compiler error, but it's going to be pointed to something right in the middle of the implementation. It's not going to be that helpful. Fortunately, this is small enough, we can work it out reasonably easily, but I'm sure you've all seen pages-long template errors that never actually get to the point. It could be quite nasty. There have been workarounds for this before, but they're quite tedious and make your compile times longer. But we've got concepts. Concepts is actually quite a big feature with lots of different things you can do. One of them is you can constrain templates with a concept. So here I'm using one of the built-in concepts, input range. Obviously you can define your own. But input range is exactly what we want here. Something that you can iterate over in a range-based for loop. That's really all we needed, at least at that level. That solves our problem. Now look, the error message, there's almost as much text, but it says there's no matching function for the call to print, so it's at the call site, not in the middle. It says the candidate template was ignored because the constraints were not satisfied when t is an int. And that's because int does not satisfy input range. It tells you everything you needed to know. They're not always as good as that, but they are getting better. So concepts are a big win, even just for error messages. But there's so much more you can do, overloading, things like that. If you are on C++20 and you're using templates, but you're not using concepts yet, please use concepts. Because you can also simplify the template syntax with the abbreviated syntax. You can use auto in much the same way that you can use in auto lambdas instead of a template, and you can constrain it with a concept. So, huge step forward for templates and generic code with concepts in C++20. All right, our ongoing example, or the vector of ints converted to a vector of strings. This is where we got to in our story so far, using std transform with a lambda. Not bad, I think. But we've still got those iterators there. Great abstraction, but they can be a little bit tedious to work with, even still. So with ranges, we can do things like std use transform. So now, we'll basically just pipe the whole container in, works out there's a range there, pulls the iterators out, does everything on the fly. And so far so good, this all works. But you probably want to put it in a vector and you sort of want to do this, but it doesn't work. This is one of the problems with ranges in C++20. Great feature, powerful feature, just not quite complete and lots of holes. So you probably want to do something like this. Std ranges copy, you've got the back inserter there again. Doesn't feel like a big improvement after all, but it is because now you can compose things much better. If we want to filter in there, you just put it in exactly in that spot, and it all pipelines together. There's no intermediate containers. Pretty nice. Ranges are definitely worthwhile. Not quite the easy win a lot of us hoped for, but they're getting better. We're going to have to move on because the C++23 train is leaving the station. As far as the standard committee are concerned, C++23 is done. It's out the door, but it is with ISO, who are still yet to publish it, I believe. But that should happen in the coming months. But we know exactly what's in it. Next week?
It's weeks from now.
Ah, okay.
There's probably 7 weeks at max.
Weeks, not months. Got you. Right. So as of 11th of September, it's going to come before the end of the month, probably. All right. You heard it here first. Whichever way you look at it, that train is leaving the station. So again, this is the slide I first showed in 2019. C++23 was a way off, but I was reasonably confident in a lot of these things. Reflection we were going to get, coroutine libraries, pattern matching, modular main. Okay, meta classes was a bit of a stretch, but I was hopeful. Of all of those, we did get more ranges, which is good. To be fair, we got std generate. That is a coroutine library, and an important one. If you want to write generator-style coroutines, they are now trivial to write. And that's a really big win. So I'm not going to complain too much about that, but we do need more. And we've got loads more features. It's actually quite a big release again. It seems to be a common theme. We don't get what we wanted, but we get a load of good stuff anyway. Deducing this, std print, ND span, more std format, all big things, which I'm not going to talk about now. They're too big. I do recommend you see Timo Dumler's CPBCon 2023, I think, keynote, where he talks about what's going to be in C++ 23. He covers those very nicely. So do go and watch that. But I'll talk about a few of these. First, though, what we didn't get. We still didn't get contracts. Which we thought, didn't make it in 20, but it's got to make it in 23, surely. Not yet. We didn't get the coroutine task libraries, and we didn't get executors. So this was what we're going to be doing for the high-level concurrency. And it's been talked about for years and years, prioritized for C++ 23, didn't make it. So let's concentrate on what we did get. And go back to this example from earlier. We were trying to use variant for error handling. We said, yeah, not so good. We want something a bit simpler than that. And that's what std expected gives us. Similar to variant, optimized for error handling. So it takes the value you want, value type you want, or an error type. You std make unexpected if you have the error case. And in use, the first part of the if is exactly like std optional. The only difference is you can now get .error out in the error case. Great, exactly what we wanted. Not perfect, though. And actually, if we go back to optional to illustrate this one, this is the example we looked at earlier. This is fine if you're just making one call and you need to immediately check for an error. But if you've got a few of these you want to compose together, as you sometimes do, that doesn't work so nicely. You end up with code like on the right. And this is only a couple of levels. You've got a few more. You start to see what we call the arrow of doom emerging, with that deep nesting and the happy path ending up in the middle. So it's not a great way to do it, especially when you can compare it to exceptions that we already have in the language. Shuffles all the error handling off to the end. Well, C++ 23 gives us the so-called monadic operations on std optional and std expected, where you can do exactly the same thing like this. You can just compose lambdas together. They do all the dereferencing for you. So you only get called back when you actually have a value. You've got and then and transform, depending on whether it was already an optional type. There's also .or else that will do the error handling part. And I say that works for std expected. There's a couple more for dealing with the error case. So that's a big win, I think. We'll see how that works out in practice. We're not so used to using this sort of style in our community, but then maybe that will change. So I'm actually going to be giving a talk in depth on error handling at CPBCon next week, where I'll go into this a bit more, including some of the problems with it. But for now, we'll move on, because we need to talk about the future. I've got sound.
It's the future.
Originally I had this for the C++ 23 slide. Things move on. C++ 23. It's sort of early days, but actually, as far as the committee is concerned, we're half done. Feature freeze is next February, so we don't actually have a lot of time to get anything new in. We already know some of the big things that we got in, and some of the things that we're still hoping for. So there's more than this, but these are the highlights. Std execution is finally in. So we talked about executors before. This is different, but it's an alternate to an alternate option for concurrency, structured concurrency specifically. It's a big, complex feature. And I think we're going to see lots of talks, trainings, blog posts, books, libraries, I don't know, dealing with std execution over the next year. I think next week at CPBCon, the very first talk is actually about std execution. It's already started. So I'm not even going to try to summarize it in one sentence here beyond structured concurrency. All right. A bit easier to take in is stood in place vector. Little thing really. It's a vector that entirely holds its memory within the object. No allocations. Fixed capacity. Very useful in certain domains, low latency, audio games, things like that. They've been asking for this for years. Finally got it. Don't know why it took so long. Linear algebra. It's another big one. But you can think of it as like a wrapper around the BLAS libraries, if you know those, for linear algebra. Fairly widely used, well respected. Not without detractors, but so far at least, this has made it into the standard. There's a couple more in there that are a little bit harder to see because they're just single characters. We've got the underscore, the placeholder. This now has new meaning. And it's something that if you don't refer to it, you can actually use it multiple times in the same scope, reuse it. It's for things we don't actually care about the variable, but you have to name it. Like RAI types that rely on side effects, like lockguard, for example. Or structured binding, where you're binding to something, several things you don't care about, one or two of them. You can use underscore there. Really nice. And they've really thought through how to be able to use just that single character and also be backwards compatible with any code that might have been using in the past. So nice job, I'm really pleased about that. It'll also be quite big when we get pattern matching eventually one day. Was on track for 26, but I think that's going to slip. The other one, the dollar there's actually a few other characters that are being adopted as legal identifiers or legal in identifiers. I think it's already gone into C. And I meant to check whether it had actually made it in or whether it has gone in. Thank you. Yeah, so we can now use dollar and a couple of other characters, I forget which, in identifiers, which is nice if you like that sort of thing. Things that we are still hoping for. Contracts, still on track, but only just. It's quite tight. I would say at this point 50-50. Looks like Daniela agrees with me. It may go into 26. It may not. We'll see. Reflection seems to be actually surprisingly ahead of that. Much higher chance of getting in. I think currently it's with wording. So barring them finding anything, I would expect it to probably be voted in November, maybe February. Keep looking at Daniela now. Knows more than me. But very strong chance we're going to get reflection in 26. And this is a big deal. This could be the game changer on par with at least 20, maybe 11. Change the way that we write a lot of C++. And this is meant to be an MVP. So not even like the fully fledged set of features we really wanted, but actually surprisingly powerful. So I'm really excited about that. StudSimD was originally part of the Parallelism TS, I believe. When I first put this up on a slide, I was going to say, and it seems to be quite non-controversial, so it's likely to get in. Last I heard, it was very controversial, so now I'm not so sure. I haven't been following that. But a few other things like that we're already tracking to go into 26. So this could actually be a very big release after all. And I'm actually on my final slide ahead of time, which I wasn't expecting at all, so that's good. So I said that I wanted to try and sort of give a flavor of how the language has evolved and also what stayed the same. That desire to get zero cost abstractions, don't pay for what you don't use, has been there from the start, hasn't always been realized, but when it hasn't been, we've tried again and we tried to improve. Get better, higher level abstractions, and also get better performance, going both ways. And hopefully I've shown that at various points we've hit that. And we're actually in a better place because of it. The language is definitely not dead yet. Moving forwards, still at a rapid pace, still a big community, a lot of interest. And yet we find ourselves at yet another crossroads, another possible Oldsmobile moment. We have challengers, so-called successor languages, saying, actually, who wants the complexity of C++? We can get those zero-cost abstractions in an even cleaner way. And maybe that's true. I think it's too early to tell, but I do think C++ is going to be around quite a few versions yet. and we'll see whether it lasts. But I'm optimistic. I think that's really the end of the talk. I wasn't even expecting to finish on time, so I didn't prepare a conclusion. So I'm going to say thank you very much.